Good afternoon, everyone. Good day. My name is Geert Krijma from the Dutch standardization body from NEN, and we are proud to host this webinar in collaboration with ISS MGE and the Eurocode Subcommittee 7 on the topic of the numerical methods. Like last year, I'm overwhelmed to see how many people attend from all over the world. With that many people present, we need some house rules. I will show it on my screen. Please mute your microphone. Use only your screen when talking. If you have questions, put them in the Q&A and don't raise your hand. You cannot see all those hands otherwise. We don't have time to answer all your questions, but we will answer all most relevant questions afterwards. And this webinar will be recorded so you can look it back. And the presentations and the link of the recording of the webinar will be sent afterwards. If you look at the program, we'll see a welcome from Georgios Katsianis. The guidance on the micro methods in the next generation from Colin Smith, the implementation and examples of new EC7 guidance from Hu. I hope I pronounced it correctly. I'm sorry. And then for the official welcome, I now hand over the word to the chair of the European Regional Technical Committee 10 of ISS MGE, Mr. Georgios Katsianis. So you can take the screen.
Yeah, thank you, Gert. Hopefully you can see my screen now.
Yes.
So yes, I would like to welcome everyone today on behalf of the European Regional Technical Committee 10 on the evaluation of Eurocode 7. We are one of the European committees of the International Society of Soil Mechanics and Geotechnical Engineering. I would like to welcome everyone to our second online event organized and delivered in partnership with the Subcommittee 7 of the CEN, looking after Eurocode 7, and of course the NEN, the Dutch Standardization Institute. So I would like to thank both organizations for their help and support in delivering the lecture today. So I have been the chair of the committee for the last 3 years or so. I'm the ground engineering discipline lead for ferrovial construction in the UK, currently delivering the second high-speed rail line in the UK, connecting London to Birmingham. So I would like to start, if I may, with a very brief update on the work we have been doing as ERTC 10 in the last 3 years or so, all the good work we have been doing. So the committee was reactivated actually in September 2019 in the European Conference in Iceland. And for the next year or so, all the way up until September 2020, we had a huge recruitment drive. We managed to completely renew the membership and fully reactivate the committee. Now we have 24 members from 16 different countries across Europe. So many of them are from the younger generation. They are from the industries, or they are the people that who will actually use eventually the second generation of Eurocode 7. We have established quarterly meetings, and we have built very strong relationships with the CEN Subcommittee 7, with the chair of Subcommittee 7, Adrian Van Setters, regularly attending our meetings. In September 21, we hosted our first online lecture on second generation of Eurocode 7, improvements and challenges, which far exceeded our expectations with more than 600 registrations from around the world. So we set the bar too high for today's event. But the aim of that lecture was to encourage, of course, geotechnical engineering professionals across Europe and the whole world to engage with the with the Eurocode 7 experts from the Subcommittee 7, the people that they're actually preparing the draft of the next generation of the code, and learn firsthand about the upcoming changes and the challenges. This side of the year, from January 22, the committee, we have been updating the terms of reference, and our main objectives are the dissemination of information about Eurocode 7 and the changes introduced in the second generation. That's what we're doing today, actually. Providing guidance and recommendations related to the application of Eurocode 7 in practice, in practical geotechnical design, assistance with organization and participation in conferences, European and international, and any related activities, workshops, etc., publications related to evaluation and application of Eurocode 7. And finally, of course, to provide the link between the ISSMGE, academia, industry, standardization bodies like NEN, to foster this development and the implementation of Eurocode 7 for years to come. In May 22, I had the honor to represent the committee in the international conference in Sydney, where we had a series of meetings, discussions with the wider ISSMGE community, representatives from industry, but also academia, trying to raise the profile of the committee and strengthen those links with the international geotechnical community. And moving forward, what we want to do is to develop a much closer relationship with the TC205, which is the Committee on the Safety and Serviceability, because they also have an interest in Eurocodes, although it's an international committee. And one of the ideas that we pursue currently is a parallel workshop in the next international conference in Vienna, along with exploring, of course, other forms of collaboration. Now, before we start with the presentations about Eurocode 7, I would like to pay tribute to some key individuals, some brilliant engineers, that they had a huge contribution to the whole Eurocode 7 project from the 80s until now. Without these people devoting their time and their brains, there wouldn't be Eurocode 7, and we wouldn't be here today discussing about a new generation of Eurocode 7. So we are standing on the shoulders of giants. And I would like to start with Niels Krebs-Olsen, of course, who was the first chair of the subcommittee 7, with Brian Simpson, Eric Farrell, and Trevor Orr. They were long-standing members of the subcommittee 7, representing UK and Ireland, respectively. Actually, Trevor, special thanks to Trevor, because Trevor was the chair of the ERTC 10 for many years, was the previous chair, so he did a fantastic job in chairing the committee for a number of years. And Brian Simpson, of course, I have worked closely with Brian for a number of years. He has also a special interest in numerical methods. A big thanks to Andrew Bod, of course. He was the previous chair of the subcommittee 7. He oversaw very successfully the work of the evolution groups of the Eurocode 7, the 14 evolution groups, which is all the work that paved the ground now for the project teams to finalize and prepare the draft of the second generation of the Eurocode 7. I would like to mention also Andrew Lees. Andrew Lees was the chair of the evolution group 4 on numerical methods. And if you are interested, I would like to refer you to his publication in the European conference on numerical methods and Eurocode 7, which provides a good overview and summary of the direction of travel and the upcoming changes. And last but not least, of course, Adrian Van Setters is the current chair of Subcommittee 7. He's doing a fantastic job. We're working very closely with Adrian. He oversees now the development and the preparation of the draft of the next generation of Eurocode 7, all 3 parts. Right. Now, I don't want to spoil anything that our speakers will present today, but very briefly, just to set the context for the day. Well, there is a number of challenges with the current version of Eurocode 7, but for me, the biggest challenge was the lack of harmonization. And as you probably know, there is 3 design approaches. There is material factoring approaches and load resistance factoring approaches, and each member state of the European Union adopted one of the 3 design approaches. And now you can see in the maps, for example, how fragmented is the map of Europe in terms of the choice of design approach. Now, some of those design approaches are better suited for numerical methods than others. For example, I know that a number of countries that they have adopted design approach 2, only for the numerical methods, they adopt the design approach 3. There is other challenges, of course, the use of more advanced constitutive models for the material factoring approach, how you apply the partial factors, if it's from the beginning as an input or at discrete stages or as an excursion. So it is clear that while in the current version of Eurocode 7, the use of finite element methods is suggested for ULF checks, there is a clear lack of a more detailed guidance. And there is a number of issues, as we said, but there is a need to better understood those issues, clarify before the ULS verifications can be routinely applied, carried out using finite element methods. And hopefully, with the presentations today, we will get a step closer in achieving that. So without further ado, I will now introduce the speakers for the day. We have an excellent lineup. I have known them both for many years. I will start with Colin Smith. So Colin is the head of the geotechnical engineering group at the University of Sheffield. He is a member, and he was a previous secretary of the Technical Committee 205 on safety and serviceability. He was a member of the Evolution Group 4 on the numerical methods. He has published several papers on Eurocode 7 and limit state design, so he's definitely an expert on the topic. And what Colin will be doing today is to give an overview, a brief description of the upcoming changes in the next generation of Eurocode 7. And and the second speaker of the day is Hoi Yeo. He's a director at COVID and also a member of the ERTC 10. Hoi is a geotechnical engineer with over 30 years of experience in the industry. He was previously, I think, for over 20 years in Arup Geotechnics, and he was the lead of the numerical skills team at Arup Geotechnics. And actually, we worked together for a brief period of time in Arup. And he's currently at COVID. He's responsible for the excellence team of numerical modeling in COVID. He has also published several papers on the application of limit states and the design approach 1 with Eurocode 7. And he's very active in several working groups and forums in relation to Eurocode 7 and numerical analysis. So that's all from me. Thanks everyone, and I will hand over now to Colin, so we'll get started.
Okay, thank you very much for that, Georgios. Can I just confirm that you can hear me and see the presentation?
Yes, we can.
Yeah, that's great. Okay. So
you have to turn your presentation on presentation mode.
Yeah, make it full screen, Colin.
Full screen, yes.
You mean it's not in presentation mode, you're saying?
Yes.
Okay.
On the right hand side low.
I think I'm just sharing the wrong screen then. Let's try that one. Is that better?
Yes. That's
okay.
Good.
Okay. Okay. Apologies for that little hiccup. So thank you, Georgios. It's a pleasure to speak to everyone on the latest developments in the new Eurocode as related to numerical methods. And as Georgios has said, I'm going to cover the main principles, and Ho will talk about specific examples. So what I'm going to do is I'll just start with a caveat. This presentation is primarily based on the latest draft of the new Eurocode of November 2021, with some additional updates. So some of these issues may be subject to change. The code is taking its final form, but it is obviously still subject to update. So what I'm presenting may, of course, change. Before talking about numerical methods, I think it's good just to get a few preliminaries in for those of you who are not familiar with the coming new version of the Eurocode. So as you know, the existing Eurocode essentially came in 3 parts that are relevant to geotechnical engineers. So we had EN 1990, which is the basis of structural design. And then we had EN 1997 Part 1, which are the general rules, and Part 2, which covered ground investigation and testing. In the new version, there are now 4 parts. EN 1990 remains, but it has been expanded or now explicitly covers geotechnical design. We have a Part 1 in EN 1997, which covers general rules. But that Part 1 has been split into 2. And the sections dealing with geotechnical structures have been put into part 3. Part 2 remains broadly the same in terms of looking at ground properties. So I'll be discussing primarily new changes in part 1 and part 3. Also, we have a number of terminology changes. I'm not going to cover them all, there isn't time to do that, but the key ones that are relevant to the presentation today are as follows. So what were described as design approaches in the current Eurocode have now become designated as verification cases, and these essentially determine the factors on actions or effects of actions, and these are defined in EN 1990. These verification cases are used in conjunction with partial material factor sets, M1 and M2, which are defined in EN 1997 Part 1. They're essentially unchanged from the current code, so M1 are essentially current unit factors, and M2 are those associated with current design approach 1 combination 2 or design approach 3 partial factor sets. So effectively it's 1.25 on tan phi, 1.4 in CU, etc. Now, we get to numerical methods. I thought it'd be useful just to take a quick survey of mentions of the code just to see what's changed. So in the old code, numerical methods were really only mentioned in passing. There wasn't really any specific guidance given on their use. I think I counted only 5 mentions in the entire code. In the Eurocode, there are many more mentions, but in particular, there are dedicated sections, definitions, tables devoted to numerical methods. And this, of course, as George just mentioned, acknowledges the fact that many engineers are using numerical methods. Numerical methods bring many advantages, and the aim in the new code primarily is to enable straightforward usage and really not constrain the use of numerical methods or make it onerous task. So what I'm going to do in this presentation is cover the key elements of the new sections in the presentation, just to give you an overview of what changes have been made and how hopefully it's going to make life easier for those of us who use numerical methods with the Eurocode. So I'll kick off looking at part 1 and the changes there. What does part 1 say? So at the beginning, we now have a definition of numerical methods. We've discussed this quite a lot in some of our task groups, and it's quite difficult to come up with a definition. For me, the key characteristic is that numerical methods are general purpose and not generally specific to a particular problem type or a failure mode. And so they're going to work best with generally applicable partial factor sets. The other key advantage is they have the power to home in on the critical failure mechanism automatically. And so it's not generally efficient to use numerical methods to evaluate a specific failure mode, as we often do with hand calculations. And thus it means that resistance factoring approaches are not generally applicable to numerical methods, since the mode of failure and thus the available resistance must be known in advance. So that doesn't really use the full power of numerical methods. So we need approaches that factor well-defined actions or action effects and or material properties. And these are what are specified for the numerical methods. So to sort of give you the initial overview, we have what's recommended in the code is a dual check for all problem types. We have a check that broadly covers geotechnical ULSs, which is a materials factoring approach, where primarily the we factor parameters before we do our calculation model or numerical analysis. And then we have one that is broadly a structural ULS, where we undertake our analysis first and then factor the outputs of that analysis, the action effects essentially. While I've labeled these as MFA and EFA, I understand that technically they're going to be known as broadly MFA approaches, materials factoring approaches. So those of you who look at that will perhaps recognize similarities to the current design approach 1, where we have 2 combinations. But the structural ULS, the action effect approach, is perhaps more analogous to what some people have been using, terming design approach 2-star, DA2-star, but we'll come to that in a little bit more detail in a moment. It's useful to perhaps reflect back on why we have 2 approaches. I know that often it's criticized, why do we have to do 2 calculations? Certainly for hand calculations, that's a bit onerous. Now that most things are being automated, it's not that challenging. You can find the reasons. One of the reasons for adopting the 2 verifications were elaborated by Brian Simpson and his paper in 2013. And the aim is really to try and achieve a more consistent reliability level across a wide range of uncertainties and actions and material properties. And what he showed is that in principle, having 2 sets of partial factors actually works better than trying to have a combined set that factor simultaneously material properties and actions. So just a little bit more detail, the geotechnical ULS materials factoring approach, you're either going to use strength reduction or a direct approach, factoring material properties directly to establish whether the system is stable with those factored strengths. In the structural ULS, we're taking an action effect. So in a retaining wall, we might be looking at the bending moment that's established in the wall, and we are factoring that and then comparing that with the available strength of the wall. So often that's going to be established from an SLS analysis and then factored. But if plastic reserves of strength are available in the system, then it's possible to take advantage of this in the analysis. And one way of doing that is to actually transfer the action effect factor from the actions to the resistance side. So essentially assign that to the structural resistance and then carry out your analysis, and that facilitates an analysis that can capitalize on plastic reserves of strength. That's a kind of broad overview. In terms of text, this is what we have a clause 8.2, which outlines the procedure for numerical models, and effectively that's just saying in words what I've just gone over in the previous couple of slides, looking at the MFA and EFA approaches, and guides you as to the various partial factor sets. So we'll have a look at those partial factor sets, see what has changed, see what is relevant to numerical methods. One thing before I go into that, just point out this is a recommendation as to the approach that should be used for numerical methods, but it's not mandatory. So looking at the partial factor sets, those 2 approaches are basically governed by this table from Ian 1990, and we have a number of partial factor sets, but the ones on the right-hand side highlighted in blue, DC3 and DC4. Now this table is slightly out of date, that those should be designated as verification cases, so technically they should be VC3 and VC4. These are the factors of that are to be used with geotechnical design mainly, though VC1 can be used in certain circumstances with geotechnical design, but these are the 2 that are recommended for numerical methods. So I'll just pick out a few of the points here. So numerical methods, it's generally going to work best if your permanent actions aren't factored. So you don't factor those before you do your analysis, and that's primarily what's listed there. It's good to see that we have specific mention of water. So there's been a lot of debate about how to deal with water and how to deal with that very well in geotechnical analysis and design. I think it's acknowledged that generally you don't want to be factoring water pressures and then feeding them into effective stress analysis. That just doesn't generally work very well, if not at all satisfactory. So here it is clear that we factor water pressures with a factor of 1. And generally we'll look at the most unfavorable conditions in terms of water table location or flow regime, rather than adopting a factor. We look for the most unfavorable general conditions that can arise. So that all works very nicely for numerical methods. For variable actions, and these are actions that are generally known in advance, they don't have to come out of a calculation. They're things that are generally externally applied, so they're quite easy to factor in advance. And so for DC3, they get a factor of 1.3, and you'll recognize these are the same factors essentially that you have for design approach 1 combination 2 and design approach 3 currently. And for DC4, we have this ratio of gamma Q to gamma G. So that's the ratio of variable to permanent factor, which comes out to be 1.1 in general. I'll return to that a little bit later for those of you not familiar with that approach. There is a factor on water here for variable, that's 1.15. The note on this table says that this is generally to be applied to water pressures, perhaps arising from wave action or currents. So these are kind of externally applied water pressures rather than those internal to the soil. So that again all works very nicely with numerical methods in general. And final factoring here, again, I'll talk about this a bit more detail later on, is that these factors are generally applied before we feed or we do our calculation model, use our numerical method. At the end of the analysis, once all the analysis has been carried out, we have factors on effects of actions, which are these values 1.35 on unfavorable effects and 1 on favorable. I'll address those a little bit later. What you'll also see in the table, I don't want to get into this in any great detail, is that some of these factors are modified according to a consequence class. So this is essentially looking at the severity of the consequence of failure. And so we do modify factors now according to that. But that's not specific to numerical methods. That's just going to change the numbers that you feed into the analysis depending on the consequence class associated with the design that you're assessing. If we then turn to the materials factors table, again, there are modification factors for consequence class. I don't want to go into those just change those numbers. You'll see that M1 are all unit factors, M2 are again the factors. You'll be familiar with those kind of numbers coming from design approach 1 combination 2 or design approach 3. There are some additional factors, so again, not directly relevant to numerical methods, but there are factors that address critical state and residual friction. But what I would say is, as well as that, of course, it's important to factor interface shear strength. There are, of course, a number of important issues around implementation of materials factors with advanced constitutive models. Here we are essentially factoring the ultimate strength of the material, but where we have advanced constitutive models, things can become more complicated. Generally, the Eurocode is not looking to address those more complex issues, and it's leaving that to the user to understand how your software that you're using is implementing the model and the potential knock-on effects of applying factors to your materials or to those parameters which end up providing the strength within the numerical model. So the only one nod to that, however, is this, that this particular factor is directed at numerical models. So where you're doing an effective stress analysis that maybe feeds into an undrained assessment, then these are the factors that are recommended. So that covers the kind of numbers that we're using. None of the key numbers have changed really from the current version, but how they're applied perhaps changes, and there are additional factors to included now in the table and some clarification, particularly around water pressures. So if we now just take a step back and just recap on ULS factoring approaches, The reason, of course, we're applying partial factors is we're trying to render the probability of an ultimate limit state to be at an acceptable low level. And so generally, we're trying to apply them at source, apply the factors appropriately to the parameters that are causing the uncertainty. In general, we need to be very clear that these can be applied to parameters before or after the calculation model. So when I talked about input factoring, output factoring, those sit either side of the calculation model. If we have input factors to apply, we apply those to our parameters, we feed them into the calculation model. That then gives us an output. We then may factor those quantities and then we do assessment. But generally, application of action or resistance factors inside the calculation model does nasty things like violating equilibrium and very hard to do within a numerical model. And that's why we have to be very clear that we're doing it at the input and the output stages. The MFA approaches, generally it's input factoring only. We have factors on materials and the factor on variable actions, and we feed that into our calculation model, go straight to the assessment. In EFA, we adopt both input and output factoring. So as I mentioned when looking at the table, the variable unfavorable actions are factored by 1.1 at the input stage. Everything else is unfactored in general. At the output stage, where we're getting something, for example, like a bending moment in a wall, those factors are, those quantities are factored by 1.35. So the net effect is that for variable unfavorable actions, at the end of the process, we've applied 1.1 and 1.35, which gives us a quantity of 1.5. That only works, of course, if the system is linear. And we do have to be aware of that. And it's important, as with using any of the code, to be aware of the reasons why we're applying factors to reduce the probability of a ULS. And if those factors are not doing the job that we intend them to do, we need to be thinking quite carefully about where we apply the factors, or are we applying at the right stage, we're applying them in the right part of the model. Permanent unfavorable actions will just feed through, and of course, favorable ones will feed through the whole process and get a factor of 1.35. And further elements that are appearing in the new code are table 8.1. So, of course, in many cases, there are construction stages to be considered when undertaking construction, and it's important to assess each of those stages as they proceed for safety. The recommendation, so the idea is that the code is trying to clarify what is often common practice or has evolved when using the current code. So the recommendation is that these EFA and MFA approaches, so these are the effectively column 1 and column 2, are adopted for each stage of the construction. In column 2, the recommended approach is to do the analysis using your what are called representative values here. That those essentially are what we're currently called in the current code characteristic values. So here we're using representative or characteristic values, and to do the stage construction with those values, and then use strength reduction procedure or equivalent to assess the safety or the ULS capacity at each stage of the construction. Column 3 provides an alternative. So if you're unable to use that, or your software numerical method doesn't allow those kind of processes, then you can apply the factors directly to the materials in advance of the analysis. I'm not going to go into this table in great detail. I think Ho is going to talk about an example where some of this is illustrated, so I'll leave that to him to look at. But key point is we've got construction stages are specifically addressed in the code now. So that is a brief overview of the part 1. I'd just like to say a little bit about part 3. So again, there are quite a number of references back to numerical methods. I'm just going to pick out 3 aspects. So we've got slopes, we've got spread foundations, and we have retaining structures. The part 3 covers also, in addition, piled foundations, reinforced earth, ground improvement, etc. But I'll just talk about the 3 key areas in this presentation. So in terms of slopes and cuttings, the code allows you to use numerical methods according to clause 7 in part 1, which is the clause that describes some of that usage. And the partial factors to be used for slopes are consistent with numerical methods as you'd expect, and most people are using. Currently, we're using design approach 1 combination 2 or design approach 3, and essentially those are the partial factors associated with verification case 3 and material properties set M2. So there's no real change there, and using those particular partial factor sets, I think generally people find it works very well with numerical methods. In terms of spread foundations, things are a little bit different. Again, it's required to verify a range of ultimate limit states, and I'm going to say a little bit more about that in a moment. But the table of factors that is given recommends that you can use combinations A and B in this table, or the single combination C. So A and B broadly correspond to numerical methods. But what you'll see is that in column A, there's a slight deviation because it adopts VC1, verification case 1 factors, rather than verification case 4. Now, what is the difference there? Well, essentially, verification case 4 is the action effect factoring approach, where the factors are like 1.35 are applied at the end of the calculation. VC1 applies those at the beginning. Now that, of course, is often quite appropriate for spread foundations. If you have a foundation, if you know what the structural load is coming down onto that foundation, that is predetermined, it's known in advance, it's not something that needs to be determined during the calculation, then it is more appropriate to factor those actions at the input stage. So you have the choice eventually, but the recommendation for spread foundations is to apply those factors in advance. But again, I think all of that works very well with numerical methods. As long as we know those action values in advance, then it doesn't provide a challenge, and again makes using numerical methods straightforward. Retaining structures are perhaps where things get a little bit more complicated. The code allows you to use a numerical method, which is fine, and it requires you to check a number of limit states. So I've copied a number of the diagrams from the code. You'll recognize these kind of failure modes, sort of global stability of the wall, failure of, for example, a prop or multiple prop, or a failure of basal heave, and so on. So all of those generally have to be assessed, and we know that, of course, numerical methods can really pick out the critical mechanism, and that there's no real need to then assess all the other processes if we're using generic partial factor sets. So just to pick this out in a little bit more detail, in terms of what the code states for assessing retaining structures, you can use the MFA approach or the RFA approach. So the MFA approach is essentially the same as table 8.1 for numerical methods. So that works fine in terms of rotational resistance. But it's useful just to take a step back and think what is the just picking up on what I said earlier about the benefit of numerical methods. Can we take advantage of that? Is that going to work within the code? So taking a step back, if we're using a numerical method to assess stability, and we might be using an incremental elastoplastic analysis and looking to make sure that deformations remain small, or we can use a direct analysis, looking directly at stability, perhaps using limit analysis, and establish that it's stable if, for example, additional disturbing forces are required to take the system to ULS. In a numerical method, if either of those are achieved, then it's implicit that our design action is less than our design resistance. However, sometimes, or in many cases, it's not exactly clear where the design action and the design resistance lie. So if we have a very complicated failure mode involving foundations, retaining structures, embankments, etc., where in fact do those lie in the system? And what is clear is that it is not necessary to establish ED and RD explicitly. If you can show in your numerical analysis that your deformations remain small, or you need additional disturbing forces to take the system to ULS, then it is implicit that ED is less than RD, and it is not necessary to state those explicitly. And that again works well with those recommended partial factors that we have in the system, and particularly for the MFA approach. For EFA, you can, obviously, if you're looking at a bending moment and factoring that and comparing it for bending resistance, you generally will do that. But when you're looking at kind of global stability type problems, you don't have to explicitly determine the ED and RD values. In addition, it's not necessary to assess specific failure modes. So for example, if I jump back to the previous slide, we've got 4 failure modes among quite a lot at the bottom here. It's not necessary to look at each one. As long as you are happy that the method will implicitly check all those failure modes using the same partial factor set, you don't have to check them individually. And there's a note in the code that essentially says in MFA, all possible geotechnical ultimate limit states are verified by demonstrating that equilibrium can still be obtained with design values of input parameters without excessive deformation or a failure mechanism being activated. So that really, clarifies that issue in terms of specific failure modes. And of course, if you look at something like a retaining wall or gravity wall, you might assess bearing failure, you might assess overturning, you might assess sliding. What often happens is you get a kind of combination of all of them. You get a bit of bearing failure, a bit of overturning, and a bit of sliding, as shown in this mechanism here. And you want to be sure that you're assessing the critical mechanism rather than assessing individual cases. So that is now clear and is permitted in the code. That's a kind of brief overview of all the ULS guidance, the key kind of elements in the code. Say a little bit about SLS. Generally, nothing much is changing here. Unit partial factors are applied. SLS usually works well with numerical methods. It's going to give you deformations that you can check. It's clearly good practice to involve a sensitivity analysis when doing SLS verification. And if you're looking, for example, at ground movement assessment, maybe with the observational method, then you might use most probable values of the soil rather than representative or characteristic values. But essentially, most I think of the guidance is weighted towards the ultimate limit state. So to wrap up my section, just come up with a few conclusions. So the new Eurocode acknowledges that the use of numerical models is becoming increasingly common among practitioners. So there are a number of specific clauses that address use of numerical methods. The primary aim is to show engineers how to be code compliant with using numerical methods. But it is assumed that the engineers know how to use the numerical methods that they're employing. The ULS verification by numerical methods, a recommended approach is to design a checks involving materials factors approach, which is essentially input factoring, and an action effect factor approach, which is essentially output factoring. And we feel that these allow the full power of numerical methods to be used in the assessment, that very general purpose approach that numerical methods provide. Guidance is given for stage construction, and SLS is essentially unchanged. So I think that wraps up my part of the presentation. I think in combination with George's introduction, we're on time. So I will pass on now to Ho for his part of the presentation.
Right, thank you, Colin. Right, I'll share my screen. Yes. Share. Right, just to confirm, can you see my screen now?
Yes, just a moment if you like. I will ask everyone to give their questions in the Q&A and not in the chat, because in the Q&A we can see it all. Thank you. Back to you, Yu.
Right, thank you, Colin, for a very clear and concise descriptions of what is now the proposals of next generations of EC7 for the guidance of procedures in numerical modeling. My parts of this seminar is to provide you with a couple of design examples of how this codes are being applied in the design of retaining structure. I mean, as you heard from Colin, I mean, he presented very details of procedures of undertaking ULS design using numerical method in the next generations of Eurocode. I mean, for my presentation, I will briefly reiterate what he said and then describe how these procedures kind of compare to the current EC7 code. And I will then present two examples of retaining wall design to show you how this is done. And because I have used, obviously, I mean, there hasn't been any sort of guidance on the numerical modeling part using the current design code. The example that I'm going to present will be based on my experience using design approach 1, which I think Colin has said that I mean is the sorts of directions of travel for the next generations of Eurocode. I'm using advanced soil model in my presentation, so I thought it would be useful to give you a bit of information or a bit of guidance on the important aspects to be considered when you use advanced soil model. And the design example that I'm going to present to you will be the Western Ticket Hall of Tottenham Court Road stations of Crossroad projects. It's in central London steep clay site. The image is showing the excavation. And the second project is a soft clay site. I mean, unfortunately, I cannot give you the details of this project. And I'll finish off with some observations and a few summaries or remarks in terms of the conclusions that I made from this. I mean, you have seen this from Colin's presentation. It is recommended that ULS or verifications be based on the less favorable of the model factor approach or effect of actions of approach or effector approach, and obviously effect of action approach is basically called verification case 4, and then the material factor approach is called verification case 3. If you look at this table, Colin has explained that. I mean, this is EFA. You take the characteristic or representative values and run through your analysis, and then you apply the partial factor on the effects of action. For material factor approach, I mean, there are two different ways that you can do it. One is the recommended one, the other one is alternative one. The alternative one is simpler. You apply partial factor on your material and take your analysis to the end, and you don't apply any factor to the output from that analysis. The recommended approach is slightly more complex, which I'll explain it using the example for retaining wall design, which will make it clearer. So in this table, this design case is now replaced by verification case. And there are proposals to change a couple of things in this table. For example, this partial factor apply on material. There's a statement saying that you can use strength reduction procedures. We intend to delete this because not all the design tools allow this sorts of procedures to be implemented, or the algorithm doesn't allow you to do this, and you have to apply the partial factor yourselves before you run through the analysis. And also there are a couple of notes added just to try to explain this more complex, so recommended method. Also, there are a couple of changes that has been proposed for the terminology used here. The material factor approach is likely to be called input factoring now, and the effects of effect factor approach will be called output factoring. And again, I mean, because of the potentials of confusion between input factoring and output factoring, there are notes added to clarify that the input factoring is a factoring of the material parameters only, but not the actions. And the output factoring is only the factoring on the effects of actions only, not the resistance. Colin also mentioned this. I mean, the EN 1990, where you can find verification case 3 and verification case 4. And basically, I mean, I'll just show this just to reiterate that, I mean, this is where you find these two verification case if you need the details. Just to make a comparison with the current Eurocode 7, we have 3 different approaches. For those who are not familiar with Eurocode, current Eurocode 7, these 3 approaches are adopted by different countries in Europe and possibly across the world. And George will show you the map of where in what countries engineers adopt which design approach, which is kind of quite fragmented. In the UK, we adopt design approach 1, and we have to do 2 combinations of calculation, which is pretty much what is now recommended in numerical modeling of the next generation of Eurocode. If you look at design approach 2, those countries that adopt design approach 2, they are fairly similar to combination 1, but for retaining wall design, they need to check for resistance factor of 1.4. Obviously, in numerical modeling, this is not possible. But if you are taking another additional sort of check, meaning that the likelihood that design approach 2 will be more critical than combination 1 of design approach 1. If you look at design approach 3, if you look at geotechnical actions, basically it is the same as combination 2 of design approach 1, because resistance factor 3 is equal to 1, which is the same as resistance factor 1. If you then consider structural approach, you will need to apply partial factor on actions and material, which means that if you consider structural action, it will be more onerous than combination 1 of design approach 1. Keep this in mind, and then we can see what is the implication later on if you were to undertake the design using the next generations of Eurocode. So, I mean, Colin mentioned about this. I mean, the next generation Eurocode is pretty much the design approach 1, combination 1 and 2. Verification case 4 is equal to combination 1, obviously with the consequence factor of 1. And verification case 3 is equal to combination 2, except obviously the so-called a bit of greater than 1 of partial factor being applied to variable load, which is coming from wave or current sorts of action. So because of that, I mean, what I did in the past using design approach 1 is pretty much, I mean, relevant to what we do in the future in the next generations of Eurocode. I mentioned that I'll try to explain the more complexes of design or the analysis of procedures when we undertake the ultimate limit state design. You saw that table 8.1, there are 3 columns. The first column is basically the first approach. You undertake your analysis using characteristic value, go through the excavation sequence, and you apply the partial factor on the effects of action. And the second approach is to use factor parameters and then go through your analysis, and you don't apply any partial factor on your forces. The third approach is you start from combination 1, and then you take so-called modeling excursions at critical stages that you consider you want to look at the forces under material factor approach more carefully. Virtually, you switch your analysis, applying factored soil properties by taking this modeling excursion. So that is easier to explain than the complex table 8.1. So basically, this first approach is so-called EFA, the first column, and the second column is the recommended approach under material factor approach, and that is taking the modeling excursion. And the alternative approach is this approach where you start with factor parameters and go through to the end. For those who are doing numerical modeling in geotechnical engineering, you know the importance of soil parameters or soil models in your analysis, and the importance of initial stress and how the ground behaves in terms of the stress path that it goes through, and the importance of choosing the right soil model for your problems, and especially when you're trying to use advanced soil model. And to make things complicated, applying all this soil model and undertaking ultimate limit state soil design, you need to know how and when to apply partial factors. And more importantly, you need to know what is the implications of applying such partial factor on your soil properties. I mean, in my work example, I'm using brick soil model by Brian Simpson, small strain hardening soil model for excavation in stiff clay. And I will also use soft soil model for excavation in soft clay. I mean, these are images of some of the major characteristics of these soil models. I won't have the time to go through them, but what I have done in my presentation is to stick to, as much as possible, stick to this color coding. When I present the result for brick model, I use a blue line, red line for small strain hardening soil model, and green line for soft soil model. Factoring soil strength, I mean, as I previously mentioned, you can directly apply it on the soil properties, or you can use strength reduction procedures. When you use simple soil model like elastic perfectly plastic molecular model, it is easier to apply partial factor. I mean, if you do your analysis in undrained total stress condition, you input it as CU or undrained shear strength, you apply the partial factor on it directly. If it is drained shear strength parameters, you apply the corresponding partial factor on it. The problem is when you have mixed undrained and drained soil and you have so-called strength reduction soil procedures, and you need to hit a correct or a right level of partial factor, and because CU and phi dash and C dash have different or partial factor, so where you need to stop if you use strength reduction procedures is critical. When you start to use more complex soil model like hardening soil model, it makes, because the strength parameters is effective strength parameters as your input, applying partial factors based on effective strength parameters doesn't always bring you the equivalent undrained partial factor if you are running it for undrained soil condition. I mean, this is an example of factoring that I did for brick model. With brick characteristics sorts of parameters, I apply a factor of 1.4. When I start to factor down the soil strength, and they are fairly close, but not always the case, depending on the soil model that you are dealing with. As I said, I mean, you need to be careful what you do, and brick model, the area under the H-shaped curves defines the effective strength parameters. I mean, if you look at Brian Simpson's ranking lecture, that is what he said. And by factoring the strength parameters, you could potentially influence the nonlinear sort of stiffness degradation sort of curves. Hardening soil model is another example. If you undertake undrained calculation, it underpredicts the undrained shear strength of over-consolidated clay at low effective stress level, and because the formulation, the stiffness is dependent on the strength and also the stress. And for one software, you see that, I mean, the dependency of the stress is based on minor principal stress, and there's another software that use mean effective stress in the formulations of the stiffness, and those are the important area that you need to focus when you start to factor down the strength. You potentially factor down the stiffness, and all that has got to be taken into considerations when you try to undertake your ULS or assessment of your geotechnical problem. Let's just go to the first example. Western Picket Hall is a stiff clay site, and it's just south of Tottenham Court Road. south of Oxford Street is a Tottenham Court Road Station, part of Tottenham Court Road Station. And the size of the excavation is 50 meters north to south, and the width is between 25 to 30 meters. It's designed as a multi-prop retaining structure with a maximum excavations of around 30 meters. Bottom-up constructions with 5 levels of temporary prop. This is the image of the finished structure. Ground and groundwater conditions, typically in central London, in that area, you're a few meters of mid-ground over terraced gravel, and beneath that London clay, and followed by Lambert bed, talc sand, and chalk. I mean, this is the properties which I'm not going to go into details, and typical so under drains of groundwater profile in central London. The first step in using soil model is to try to get a good understanding of the performance of the model with test data. This is triaxial compression, isotropic consolidation, isotropic undrained tests under compression and extension, and for brick model and hardening soil model. And then you then need to have a clear indications of whether they match the stiffness profile. Obviously, these soil models are isotropic model, and you match the compression side, but not the extension side. And those are the compromise that you have to take. I mean, if you are doing numerical modeling. The way I compare these results is that, I mean, I used the original design, which is undertaken using Oasis Fru software. And this Oasis Fru software is a pseudo finite elements or wall design software. It's not finite elements, but it's conventional sort of design, retaining wall design software. What I did was that I extracted the envelopes of the bending moments from the Fru program and normalized it to the maximum bending moments of the envelopes, which is now plotted in black. When I undertake analysis using either soil model, brick and hardening soil model, I did the same. I normalized it by factoring it with the maximum values of the bending moment from Fru. And what you get is that anything that is lesser than the Fru envelope is showing that, I mean, the analysis is I mean, slightly more economical in terms of design compared to Fru source of output. And then when I compared it against another design approach, for example, this is verification for when I apply partial factor on the effects of actions. When I apply the partial factor on material, then I did the same, and you can see that, I mean, the distance between the black and the color line show you how the relative magnitude of the bending moment, which means that, I mean, for this alternative material factor approach, I mean, this is less critical than the effective factor approach, so calculation. And that is how I have compared them, and I compare all the results based on that approach for this particular soft stiff clay site and also the soft clay site. So I repeat this alternative material factor approach and repeat that you use with the recommended material factor approach, which is the recommended source of sequence under verification case 3, and you can see that they are still within the black line, meaning that this is less critical than the first case, which is the effective factor approach. So from this, I mean, sorry, the last bit is this. I mean, there's another part of it which, when I mentioned about factoring strength, and then you can factor down the stiffness as well. And when you look at the effects of factoring down the stiffness, brick is giving us a more critical soil design than hardening soil models. And you need to be careful when you factor down the strength. You might be factoring down the stiffness, and all that has got to be carefully considered. I mean, there's a possibility that, I mean, when you factor down one of the soil model, you change the characteristic of the stiffness profile, and it can lead to some unforeseen sorts of output. In conclusion, for the stiff clay site, I mean, verification case 4, or the effects of effect factoring approach is governing the design. And factoring material from outset or taking the design excursion is not critical in this particular design case. And under this verification case 3, when you factor both the material strength and stiffness, and it becomes more critical for one advanced soil model but not the other one. So those are the sorts of considerations you need to take when you start applying factor on ultimate limit state soil design. The second case is the soft clay site. It has got 17 meters of soft clay, and the excavations is about 28 meters deep. And beneath the soft clay, we have a more competent soil. And the design has been done using a more column model. And for combination 1 or verification case 4, I mean, that is a more critical case. And for combination 2 or verification 3, and it's less critical. But you can see that, I mean, the positive, when we undertake the verification using verification case 4, the critical part of the forces is on the positive side of the bending moment. As we apply partial factor on material, with the behavior starts to switch, and the negative moment is growing and growing, and that is for more column model. The way I have verified it using soft soil model is to, first of all, derive a set of parameters, the strength parameters that match as close as possible to the more column model. Undrained shear strength, which is 5 plus 1.5 Z, which is very soft soil material. And 1.4 factor is applied on the undrained shear strength on the more column model. But when you apply the partial factor on the effective strength parameters of 5 kPa and 22 degrees, again, you are not getting an equivalent of 1.4. The partial factor, the equivalent partial factor is between 1.3 to 1.4. I plotted the same sort of output, comparing the more column and the soft soil output, and you can see that effective effect factor approach or verification case 4 is governing the design, and the material factor approach are less critical, whether you undertake it using alternative or recommended method. So in conclusion, for the soft clay site, again, I mean, verification case 4 governed the design, and the verification case 3 by factoring material from outset or taking excursion is not critical. It's important for me to stress that, I mean, verification case 3 is not important here is because possibly it's because the geometry and construction sequence and the ground conditions that I have used to present this design case. I mean, your design may be governed by the verification case 3. So you must check both verification if unsure. I mean, obviously the recommendation of the code is that you virtually use the most unfavorable out of the two design approaches, or out of the two verification cases, and that is a critical sort of point that you must take away. If you are not sure, check both of them. Coming back to the comparison between the existing and the new code, for those who are using design approach 2, you can see that they are equal to design verification case 4 or combination 1, but you have not checked the combination 2. So moving to the future, you will have to check combination 2 or verification case 3. Obviously, until the next generations of Eurocode is rolled out in the next few years, you don't have to be worried about it. You can still adopt what you are doing, but these are the sorts of changes that you have to make. For those using design approach 2, you have to do an additional verification case 3. For those who are using design approach 3, for geotechnical actions, you only check it for verification 3, and then now you have to check it against verification case 4, because your structural action, which is applying partial factor on action and material factor, is maybe more onerous, or it is more onerous than the verification for case 4. So you have to virtually do a verification case 4 as to replace your structural action sorts of verification. Conclusions: next generations of Eurocode 7 for numerical modeling, the procedures is equivalent to the current design approach 1. Colin has said that, I reiterated that. For the construction sequence and ground conditions that are presented, I mean, verification case 4 is more critical for both soft clay and the stiff clay site. I mean, I must emphasize that that is based on what I assume as the construction sequence and the ground conditions. And verification 3 is not critical either, whether you apply the partial factor from the outset or taking modeling excursion. Under the current design code, I guess, I mean, I've mentioned it, design approach 2 has not taken into consideration verification case 3, but if you apply a resistance factor of greater than 1, it might cover your verification for this combination 2. For design approach 3, it is not conservative if you consider the geotechnical actions, but it's too conservative for structural design with partial factor on actions and material. So from that, you can see that, I mean, between now and then, there are changes to the next generation of Eurocode that you will need to start making the change when it becomes the replacement code in the future. That's all that I have to say. Thank you. Oops.
Thank you, Wei. I will give the word to Georgios for the questions in the Q&A.
Yes, thank you, Kurt. There is, yeah, there are a few questions on the Q&A. Okay. Right, so there is Andre. For diaphragm walls, the effect factoring approach yields usually larger bending moments than the material factoring approach. don't know if that's a question or an observation. And in SLS, we usually neglect the non-linearity in the structure due to cracks, etc., and creep. Therefore, we underestimate the structural deformations. That's from Andre, his observations. And there is also from Amir, asking about the observational approach, if we need to apply any factors in the analysis, if there is any guidance in the Eurocode 7. I don't know, Colin, you want to respond to that about the observational method?
I'm not that familiar with the observational method. I know it's addressed more extensively in the new version. I don't know whether you're you have more experience in that one. You could answer that one better.
I can try to answer that. I mean, for observational method, I mean, you still need to fulfill all the requirements of the code requirements, despite the fact that you use most probable sort parameters. I mean, eventually you still need to make sure that your structure can fulfill the ultimate limit state, and with your construction sequence and the contingency plan that you put in place, there's no shortcut to that, unfortunately.
There is a comment also about the design approach 1 combination 2, that you might not reproduce the in situ state with the factor friction, the factor material properties.
Yes, I mean, you're right that, I mean, that's why, I mean, this combination 2 taking design excursions, or the recommended sort of approach is is preferred, because you are following the stress state in the ground as close as possible to the characteristic value, and you only take the excursions for critical stages, and at least that doesn't start off your model from a wrong in situ stress state. So those are the sorts of things that has been taken into considerations, and the reason why the excursion sort of method is recommended instead of the alternative where you factor soil properties and carried out the assessment from the outset.
Yeah, because at least you start from the correct K, not from the initial stress field.
Yes, yes. I mean, so the recommended ones give you the correct source stress state from the beginning. Classical cutting soil can, in case of consolidation, due to superior model memory reset caused by unloading or round off error. That is something that obviously, I mean, if you want to if you want to give us more detail, then perhaps, I mean, that I can take that outside this discussion.
Well, that's more for SLS, no? I don't think it's related to ULS, is it?
I think that this could potentially be you mean model memory being the stress history, or? Yeah,
maybe Andre can clarify on the Q&A.
Yeah.
With a new comment on that.
I mean, soil models. I mean, the important of understanding how your soil model behaves is critical in what you do in numerical modeling. And for example, what I mentioned there is under predictions of undrained shear strength and things like that, and it is critical that all this detail of how the algorithm works, you need to have a good understanding of it. And obviously, the more you use the soil model, the more you have experience.
There is also a question about the phi C reduction. How exactly does the phi C reduction as a method tool implemented in most software packages fit into those approaches?
I mean, C5 reduction is pretty much a black box, depending on what type of soil that soil model that you're using. Certain soil model switch over to more column and not bothered with the behavior or the complex behavior of the advanced soil model, and just do the C5 reduction gradually within the software. So again, I mean, this sort of approach, you must have a good understanding of how the soil model that you use and how the algorithm affect the behavior of your soil model, whether it is just directly applying a factor onto C5 and not bothered with the other characteristic like change in stiffness and all that sort of things. I mean, you need to understand that. I mean, I cannot give you any sort of direct sorts of guidance unless you have specific sorts of details that you want to share with me. Then I can try to have a look at what possibly be the algorithm that they've used.
But most of those tools, they drive the system to failure, right? The FIC reduction.
Yes, I mean, they keep doing it. But the problem is that, I mean, what does the soil model do? I mean, that is critical. It's not only they won't drive it to failure, but you need to understand when in the process of driving it to failure, what is the actual calculations that it's doing in the background.
Yeah. There is a question from Suzanne. Do you have any insight into how the new Eurocode 7 approaches numerical modeling, but for rock engineering?
Not me.
Yeah.
We normally try to simplify the rock into. It depends on the type of rock. I mean, if the rock is heavily jointed, I mean, we can use approximations of the rock model, but not the massive soil rock type of modeling. I'm not very familiar with that.
Yeah, I'm not that familiar. I know there's a lot more gone into the code about rock engineering because the current code doesn't have very much on that. And in the appendix, there is a range of recommended analysis methods for rock mechanics problems, which tend to be the sort of limit equilibrium ones, slip circle type approaches. But again, it very much depends on whether you've got very jointed rock or monolithic blocks. My suspicion is that getting the rock engineering into the code has been quite a task, and getting numerical methods into the code in a coherent way has also been a task. So that is something that perhaps has not quite got there at this stage. I think, any of the methods. If you feel the numerical method that you're using is appropriate for rock, then you would apply the techniques that are in the code. But again, it depends on the material models you're using. But if it's simple friction models in blocks, we did have a debate a couple of days ago about the Hoyt-Brown model and how you would factor that. And again, I think it's having an insight as to what parameters control that and how you interpret. How you're trying to get safety into the system. So you might take an approach that the Hoyt-Brown model is providing a nonlinear yield envelope and simply scale that in the same way that you'd scale C and phi models, because you can bracket a nonlinear failure envelope by a whole load of linear C phi envelopes. But to answer the question, I don't think there is specific guidance given in the code that I'm aware of.
Right, there is another question. With the method where one increases the loads according to VC3, but not the bulk density, and then runs a FIC reduction, being a allowed variant of the material factoring approach?
So I'm not quite clear. I mean, in VC3, we're not really factoring anything apart from the variable unfavorable actions.
Yeah.
So I'm not quite clear
So
what's there?
it's material factor. So maybe in principle the question is if we can run phi C reduction instead of applying the factor, which I think we discussed previously about the phi C
yeah, I
reduction
mean,
tools. Yeah.
if you have a model to run under combination 3, so-called verification case 3, and you want to run the C5 reduction, you can. The only problem is the one that I highlighted there. If you're laid soil with drain and undrained soil input CU and phi-C-, then where do you stop the C5 reduction? Because C5 reduction, I mean, some software allows you to set a partial factor that stop the computation. But if you got CU input and then you need 1.4, and then phi-C-, you need 1.25 on tangents of the phi-, then you don't know where to stop. So that is what is critical there when you do the automated sorts of C5 reduction or strength reduction approach.
Right. There is another question from Eric. I noticed that under VC3, consequence factor is not applied on the loading, but only on the material strength. Is there any reason behind? Also, how is the consequence factor determined? Is it necessarily only 1.1, 1, or 0.9?
I can have a go at the first one. I think I'm not directly clear the reason, but I think within VC3 and VC4, this idea that we're applying factors either primarily to material properties or to actions, so that we can ensure that we achieve the correct reliability over a whole range of uncertainties of both action and material properties. So that the underlying principle is that essentially either you're factoring material properties or you're factoring actions. So this consequence factor is obviously more logically applied to those parameters that already have factors on them. Those that have unit factors, essentially we're saying don't factor them. So applying the consequence factor to that doesn't really make sense. So that you've got, in VC3, you've got the consequence factors on the material factors. In VC4, it's on the action factors. With regard to 1.11 and 0.9, those are what are in the code. I think they can be varied in the NDP, but I don't know if there are any variants allowed on that. Don't think my colleagues know either.
I don't think there is an option to vary that in the national annex, but we can double check it.
Yeah.
I think it's fixed.
Right.
Could you please elaborate which set of partial factors should be applied in the design of slope, stability, and finite element analysis, like fluxes?
So I think for slope analysis, it's VC3 and M2. So it's that's the recommended approach for slope analysis. So you're not factoring any actions, any weights, only variable and unfavorable actions, which are generally external, and you're reducing the strength.
There is a series of questions from Ed. Groundwater level in the design is one of governing factors in the design of retaining wall and slopes with soil nails. So the method to determine the design groundwater level is critical. How to determine the characteristic value of design groundwater as recommended in Eurocode 7. How to interpret worst credible groundwater conditions. Are there any differences in the design groundwater in ULS and SLS cases? If some groundwater monitoring data is available, what assessments are recommended to interpret the data and obtain design groundwater? It is not uncommon to encounter a situation of no groundwater monitoring or no groundwater capturing monitoring. How should design groundwater be determined as soon?
So I think this relates to my comment about groundwater. I didn't have time to go into it in detail, so I made some very general comments about worst credible groundwater conditions. There is in fact quite a lot of guidance in the code, very specifically directed at this, that covers these areas in a lot of detail.
Actually, Colin, we are planning to organize a separate event, an online lecture only on groundwater, because that's a huge topic.
Yes. So I think rather than trying to answer that here, we'll leave it to that meeting, because there's a whole range of issues, and really it helps to have diagrams and slides to illustrate those.
Exactly that. So we will have a dedicated online lecture only on groundwater with experts from the subcommittee 7 on the topic. Okay. Is the idea of output factoring similar to the global factor approach? I don't think it is. No.
I don't think so.
No, we spoke about the terminology. When we say, and that's exactly the pushback from us, because the terminology output factoring will cause this sort of confusions to people.
Yeah, I mean, it might look like that in some cases, but it isn't.
Refer to table 8.1. What is the recommended approach for slope design, column 2 or column 3? Will there be any difference if the slope is reinforced with nails or anchors? I think we answered that about the slope stability. No.
Yes, I think it's only if you're using a sophisticated model and the strength, if you're using strength reduction, for example, it leads to different conditions. But at the end of the day, so unless the pathway to failure is important, sometimes it is, but sometimes it isn't. And I'm not sure there's going to be a lot of difference there. And I'm not sure if you've got reinforcement in there. Again, it depends on the model you're using.
There is a question from Elnas, I think directed mostly to her. Considering the fact that you concluded VC3 has not been critical, I think it is not necessarily the case with the current design approach 1 combination 2, because we see, for instance, that design approach combination 2 can be critical check for the global stability of a cover dam in finite element modeling. How do you see that? I think that's exactly what you said, Jorge, no?
Well, what I say is clear. I mean, it doesn't mean that combination 2 doesn't is not critical. Combination 2 can be critical depending on the soil type and how you build the retaining structure, and that's why I put on the red warning there. I mean, based on the conditions that I presented, and in terms of ground conditions and construction sequencing, combination 1 has been critical for both the cases, but it doesn't mean that is the case. I mean, you need to be sure that, I mean, you need to make sure that you select the most critical one and carry on with it. If you're not sure, you need to carry out both combination in order to make sure that you cover both the combination in your analysis. It doesn't mean that combination 1 is critical.
It depends on the mobilized strength, no? Right?
It's kind of
soil geometry sequence. How much soil strength you mobilize?
Yeah, I mean,
the more you mobilize, the closer you get to make it more critical.
For the soft clay, I was expecting it for combination 2 to govern, but because of the ground conditions that I've got in that model, we have a competent soil beneath that 17 meters of soft clay, and that possibly dictate how the retaining wall behaves, because it is a multi-prop retaining wall, and you go down gradually, and if you've got more competent ground beneath, and if you start to model it with maybe 25 meters of soft clay, you might see a different picture. and it's a function of how much you mobilize, and it's a function of how much the ground pushing on the wall. And at the moment, for that particular case, it is not critical.
Yeah, and I think, I mean, in general, often VC3 or DA12 is more critical for global failure. But as you said, Ho, it very much depends on your ground profile and the construction method. So that's why we check both, basically.
Yes.
I think generally DA12 or VC3 is going to guard you against global stability, and VC4 is more likely to govern the structural side, but not always. So yes, we have to do both.
Right, let's move on. In applying the partial material factor 1.4 on a drain shear strength, any recommendation on the value of shear strength where this 1.4 shall be applied to?
Usually it's applied to characteristic value of the undrained shear strength, and you need to decide what is the characteristic values of the soil that you are dealing with. And obviously, if you look at the current Eurocode, is the characteristic value is the cost estimates of the soil properties that affect your limit state. If your limit state is if you have experience in the past that your limit state is governed by certain sets of parameters, then that sets of parameters is what you need to factor it down from. I mean, for most of the cases, we call it characteristic, and it's 95% confidence level. But some of the design, I mean, for example, if you look at some of the power design in the UK, I mean, all the established sorts of design profile is based on mean value, and then you can then take mean value as your profile, and then if you want to factor from that point, you factor from that point. So it's a function of how you design your structure and how confident you are in terms of your soil properties, in not exceeding the limit state that you are dealing with.
Right, there is a question about the two material factor.
Okay. I think maybe I've not made it clear. I mean, hardening soil, small strain hardening soil model is one type of advanced soil model, and brick model is a different soil model altogether. So I don't. I mean, there's no. I guess, I mean, latest version is where you find the latest version in the software. I don't think that they have changed much from the two model that I'm familiar with.
Then there is a comment. I noted numerical model used should not be specific to a particular failure mode. How limit equilibrium method in overall stability check using slope W fits in Eurocode 7?
Okay, so that's an interesting one. So limit equilibrium methods in classical slope stability analysis are specific to particular type of failure modes, but do search for a large range, and sometimes these methods are able to pick out non-circular mechanisms. I think it doesn't really matter, because slope stability, the recommended approach is VC3, which is recommended for numeric models. So they're essentially the same. And limit equilibrium is a method that is permitted in the Eurocode for slope stability.
So yes, we can still use slope W. Why would recommend to apply material factors only in specific states, since partial factors are due to cover uncertainties in a specific aspect like soil parameters, and in theory there should be possible values? Why is the uncertainty addressed only at discrete construction stages and not right from the beginning? It seems more like an old general safety factor than a partial factor applied to the material properties.
So this is more the recommended MFA approach, and obviously we discussed it before, and we need the ground to have the correct stress state, and then you as you excavate, you have got quite a few sequences. If you start off with the factored soil properties, the stress state in the ground might not be correct, and then you can get any results that you don't want. So if you maintain the stress state in the ground to be as close as possible to the stress state in the ground, and start to look at critical points where the excavations or the construction tends to give you the worst condition, then you look at the material factor effects of that particular stage, and that is more sensible. And all this sort of discussion has gone on for a long while, and the reason for selecting this as the recommended approach or method is because of the fact that you maintain the correct stress state in the ground as you progress your excavation, and only apply partial factor to stages where you want to look at the consequences of the uncertainties in the ground. So that is the background to it.
How would you approach critical state soil models with input material factoring, as there is no clear strength parameter value available upfront? That's similar to the brick, no?
Yeah, it's similar to the brick model. I mean, you need to find a way of doing it, and brick model doesn't give you phi dash. Brick model only gives you the degradation curve and all the rest of the parameters. You have to find a way to do it, and I'm sure that, I mean, whatever model that you use, there will be a way of determining the strength parameters, and you have to use that to see how you can factor it. And that's why, I mean, understanding the model that you're using is extremely important.
Yes, and the Eurocode 7 cannot possibly give guidance because there is a large number of constitutive models, and there are new ones popping up every year. So I think what's important, the principle is that the user need to derive a set of input parameters that results in a factor strength in accordance with what the Eurocode 7 suggests. That's the only way. But that's, yeah, it requires a bit of extra effort to do this calibration exercise up front.
Yeah, I think, I mean, as I mentioned it before, I mean, different software possibly program similar type of soil model in a different way. And I mentioned about this hardening soil model where the stiffness is a function of minimum or minor principal stress, and the other software use a mean effective stress. So those are the sorts of things that all the users needs to be aware of.
Yeah. When you factor phi dust peak by 1.25 and phi CV critical state by 1.1, then you may have strange situations. Well, that's true, but you need to use engineering judgment, I think, and the factor peak cannot be less than the factor CV. No. So
yes,
I think,
I think it depends on the model that you're using. I'm guessing this isn't necessary. You know, these factors are not necessarily directed at numerical methods, but if you're using a numerical model that will model peak and critical state at the same time, then you've got to think quite carefully about how those factors are implemented and how those strengths are derived. But I think that's obviously a change or an addition to the current code, that it's a nod to the fact, I think, that critical state parameters are often regarded as more reliable than peak. But yeah, it's again down to the model you're using. If you're using a very simple model, I think it's quite straightforward. If you're not, then it's something you've got to be aware of.
In VC4, initial stresses should always be based on reduced strength parameters. Otherwise, failure points could occur.
I think it's the opposite, isn't it? I mean, if you use the normal or characteristic strength, you have less chance of failure point. I mean, if you have failure points, I mean, your model is not right because the in situ soil stress state should not have failure point in the ground, or theoretically should not.
Is MFA approach limited only to models which define the strength by using the parameters foreseen by Eurocode 7, C dust and phi dust? For example, North-Sound or similar models which use different approaches to define strength can be used only by EFA approach. Thanks. I think we discussed this about the more advanced constitutive models. No, it's the same pretty much approach.
Yeah, everybody needs to, or whoever that use the soil model needs to understand how they can apply it with MFA.
Yeah. There should be also a comment on dilatancy. For phi, certain value depends on mesh size. We will not get a unique solution.
I think that's probably beyond the remit of the Eurocode. That's a complicated issue. We know that if you've got non-associativity, then you don't necessarily get a unique solution, and you can get oscillations in your results. So I think that's one where it's down to the user of the model to know how to use that best and to interpret those results.
And from France, are there any recommendations related to constitutive models where strength is void ratio dependent, hypoplasticity, etc.?
I think we are getting to an area where it's getting very soil model focused, which is not part of what we are trying to get to.
Well, the Eurocode 7 cannot substitute the expertise in numerical analysis and the knowledge of the modeler. So that's not the intent, to give a detailed guidance. Otherwise, we will need hundreds and hundreds of pages just on the section on numerical methods. Yeah. So no, it doesn't go in that detail to separate between different types of advanced constitutive model to give separate guidance for those. No.
Again, the next one is creep time.
If we have a time-dependent constitutive model creep, how would this approach being applied? It's same sort of questions, right? About different types of constitutive models. From Ronald, there is always a lot of discussion about applying partial factors or strength reduction in undrained layers. Sometimes applying strength reduction in combination with undrained behavior leads to factor less than 1, even if the initial situation is stable. So this may lead to unrealistic safety factor. Should this be done rather than drained then? What are the recommendations of the presenters at this point?
Well, I mean, usually if you factor your soil strength, then you are unable to run your model to convergence. It's either the whole system is not stable, or the algorithm or there are some numerical or problem in the algorithm. I mean, some of the model that I've run, you see displacements of 5 millimeters, and then it says soil collapse, and those are potentially numerical issues within the software. And if you really, when you run it and then you don't get convergence, and then possibly the whole system is not stable. So I would say that, I mean, if you really can't get the factor of safety of more than 1, after applying your factor, if you investigate your model and it is doing the right thing, but not able to get the convergence and you get the failure sort of mode happening in the model, it's likely that you are not achieving your partial factors or requirement. So you need to then make sure that you can get to the you can change your design to get to your converged type of model. That is assuming that the model runs in the sensible sort of way, and you see that yes, there is a failure.
There is a question from Richard about the combination 1. He was surprised was the critical. For major retaining wall analysis that I encountered, combination 2 would determine the design. Was limit equilibrium method or subgrade reaction method valve used for the comparison?
Well, I use through and I use more advanced soil model, and then as I said, Richard, I mean, you could get combination 2 to govern depending on the soil type and depending on the construction sequencing and all that. It doesn't mean that C1 always govern. That's why I've said that before. I mean, usually, from what I have seen, usually in stiff,
especially in the UK,
London stiff clay, London clay, and in more competent soil ground, combination 1 tends to govern. But you never know. It depends on what you are building, and if you're doing something very, very ambitious, and for example, if you excavate, 15 meters with a single prop at the top, or without a prop at the top, then you might get C2 to govern because the soil strength just being fully mobilized. So it's not black and white sort of stuff. You need to confirm which is more critical and take it from there.
Well, you need to do both, so you don't need to second guess. So it doesn't really matter if it's the one or the other. You have to do both, and you will find out.
Yes.
So yeah, it's not good to rely on previous experience and disregard one of the two.
Yes, that's right.
Following up, the partial factors applied in the design of slopes using fluxes, should strength reduction procedure be used then for slopes stability analysis?
I think that's similar to a previous question. You know, the code says you can also use limit equilibrium. I think it depends on the numerical model and how you expect the soil to behave on its pathway to failure. You may need to use strength reduction, but even then, just directly factoring it will probably give you similar results. It depends if the initial conditions are important.
Gareth,
it's about 5 o'clock. Yes.
We have 10 more open questions. What can we do? Can we follow up on them?
If Colin and Yui have time enough to answer them, that's no problem for us. But I know that you will have to go to another meeting.
Yes, we need to finish sharp. Yeah.
So it's a question from to you and Colin. Do you have some time to finish those questions?
I'm okay, but
yeah.
Colin,
I'm okay too. Yeah.
Yeah. Let's carry on then.
Let's carry on.
Okay, but I will have to leave because I have a work meeting in 2 minutes. Yeah. So.
Yeah.
Thank you, Georgios.
Okay. Thanks,
thank you very much, Georgios. And
thank you, guys. Thanks, everyone.
See you. Okay. Thank you. Bye. So the next question is from Darius. Do you know whether the required minimum values of the reliability of index beta as per EN 990 are reached using the new numerical modeling methods? The numerical methods potentially allow to lower the model error. Therefore, perhaps the material factors could be reduced to keep the same reliability. I don't know for whom the question is, but I hope one of you can answer it.
So I'm trying to work out I think the question is about is it the question that if we use a numerical method, we have a more accurate result. So we got a lower model error, and therefore the material factors could be reduced to keep the same reliability. So I think this is probably about model factors, and there are clauses in the code more detailed, I think, about model factors, but I don't think there's any general guidance that you would get away with lower factors on a numerical model at present. I think that's my perspective. It's an evolving thing. We've got to you know, do more work looking at the relationship between numerical model outputs and you know, conventional limit equilibrium approaches, and of course it's going to change depending on the numerical model that you use. So correct me if I'm wrong, I don't think there's any guidance that says you can use lower factors with numerical methods.
Okay.
You might be able to do that. You might be justified in using a model factor that's lower. The guidance says you should use a model with an appropriate model factor that ensures that you are conservative.
Okay.
but more than that, I cannot say.
Then we keep it for this. Yes.
Can I add one thing, a line or two? Basically, partial factor, you never get it to reduce. And model factor, depending on who you talk to. Some are saying that you use numerical modeling is a lot more risk in it because of the fact that, people are not comfortable with it, and they might want higher modeling factor. So it's a double-edged sword, or what you call it.
Okay, thank you. For the next question, it's maybe a statement. In the comparison of DA1C1 and DA1C2 in example, the finding covered the stability safety factor, since it's, if I'm wrong, not only BM is compared.
Of course, the whole thing is in terms of the model that I have done. The stability, overall stability is all satisfied. I'm just outputting the bending moment just as the guidance of the criticality of the design of the retaining structure. Yes, I would say the overall stability factor safety is covered there.
Okay. Then the next question is there any special provision for material factor on strain weakening clay? Oh, sorry, I skipped one. I'm sorry. Yeah.
Strain weakening clay. It's basically this is the what do you call it? Softening soil behavior of the ground. You pretty much. You do have soil model that can handle softening soil behavior of the ground, and if you have that model, you apply the partial factor. You go ahead and do your work. There's no differences or there's no difference in partial factor between different soil model. If you use soil model to do undrained sorts of calculation, and then you rely on undrained shear strength, it's 1.5 calculation is 1.25 on tangent delta. And if your model can handle strain softening, then you are covered there. The unfortunate, if your model cannot handle it, then you should be using it, unless you factor it down to the so-called soft, the residual strength as your soil model, but that won't be appropriate either.
Okay. Then the question I skipped is the verification of structural forces and/or anchors, struts, forces, and standard check in the VC3 factors on soil strength.
I would say so. These two combinations, you're saying there's uncertainty either on material properties or on structural force or actions. So you have to check both. If the soil is weaker than you expect, then you have to check that the structure can stand up with that weaker soil, basically.
Okay. Then the other question is there any advice for soft soil, since if applied a material factor, the soil became very weak and may not stand, while in the real case, the slope can stand. Who issue? I don't know if I say it correct, but I hope you understand the question.
I think it means without, probably, is shorthand for without.
Oh well, I mean, so that is the whole thing about managing risk in geotechnical soil design. The partial factor is there to protect situations where you do have uncertainties in the ground, and the factor is there to protect you. Yes, I mean, you can factor down the soil and then it doesn't stand up. Yes, I mean that has happened many times.
Okay, then the next question is what is the verification procedure used to back analyze failure case, and any lesson learned? Maybe the next statement is an agreement of France, but
I don't quite understand where that is going in terms of back analyzing failure case. I mean, you can back analyze a failure by getting to a point where you know what is the failure that happens at the set strength. So you only do that, and then whether then you use that set strength to redesign your new structure, then yeah, I mean that is your ultimate strength that you can back analyze. Yeah.
Okay. Then from Ivan, as an example of retaining walls calibrated 2D models, best performance against measures used to be the one that assumed plane strength parameters instead of triaxial. It could be interesting to include some recommendations regarding the model boundary stress, strain, conditions for the representative of the terrific strength parameters, maybe?
Oh, well, I mean,
it's a lot of words, but
yes. You are right. I mean, the triaxial test, I mean, according to my mentor, is the wrong thing to test the ground, but that is where we are, and a lot of ground structure that we have doesn't follow triaxial. Plane strain, I mean, the plane strain, I mean, direct shears and extension, compression, that sort of thing. But how do you test those big structure and to get all the mode of deformation correctly represented in the lab? Not possible. So what you do is that you test it using triaxial and then calibrate it against your soil model. And then when you do boundary values or problem, you model your structure. Then if you have case history that measurements, then you can say that, well, I mean, yes, I mean the direct source of input from lab test results, it doesn't fit the measurements on site. Then you calibrate, you try to improve the input parameters so that you get a so-called characteristic value that you're comfortable with. One-to-one sort of input will never get you anywhere, especially triaxial to real life sorts of structures or performance. And all the researchers know that, I mean, you do single element sorts of tests, you never have that same parameters that represent site sorts of measurement.
Okay, thank you. Then next question, Euro provides factors on soil properties, but it doesn't describe factors for Young modulus. Can you please explain what factors to be taken in DA1C1 and DA1C2 on soil Young's modulus?
I mean, the factor that we apply is only on the strength parameters, not even the density. So it's only cohesion and friction. There is no recommendations on factoring strength. I mean, I included that stiffness or factoring was because in the past, I mean, when you have Syria 580 recommendation, there is a clause in all Syria retaining wall design guidance that says that because of factors the soil strength, the stiffness drops. Hence, you need to allow for some factoring of the stiffness. But since then, I mean, the new Syria revisions of 760, that has been taken out, and there is no recommendations of factoring the stiffness in retaining wall design, and I've included there was part of the serial 580s of clause that requires or that recommend that you factor stiffness as well. But I mean, no, I mean, current Eurocode, future Eurocode has no guidance on factoring stiffness. We shouldn't be factoring it.
Okay, thank you. For the audience, I think we will wrap up with those 4 questions now present, because otherwise we are running too far out of time, I guess. So I will start with the question. The VC3 for slope design, if soil reinforcement such as soil nail is modeled in slope, and am I right that resistance factor set R1 shall be applied to the soil reinforcement?
Colin, do you know?
That's an interesting one. I'd have to go back and look at that. So I think on the wider question, it's interesting that, for example, things like anchors and nails, you might field test and you might get resistances measured directly, and it's good to apply those in the analysis. But you end up with a hybrid kind of analysis where with a numerical method, you're trying to apply factors to material properties or to actions. So I'm afraid I don't have a direct answer for that at the moment, but I can look into that in more detail.
Okay, thank you. The next question is, are there recommendations regarding the design in seismic areas and how to do a numerical static calculation excursion to apply the safety potential factors out of EN 1998-5?
That is a complex one. I mean, in seismic soil design for retaining structure, for example, I mean, depending on how complex you want to make it, if you do a pseudo-static type of calculation, I mean, it's more straightforward in finite elements modeling. If you start to do dynamics based and you need to do time history and all that sort, things gets a bit more complicated. Obviously, I think EN 1998 requires you to design it as ultimate limit state, and meaning that you still need to have the full factor of safety, I believe.
Okay, thank you. And last question. Sensitivity analysis as far as stiffness is concerned is probably the best tool to assess where we are with our results. So it's more a statement. Do you agree?
Yeah. Well, I guess, I mean, it's the functions of how critical or what sorts of structure that you are modeling, and a lot of time, I mean, when you design soil structure, soil interaction, you provide stiffness to structural engineer. Once you get the right calibration, you say doubling, halving stiffness, you don't normally get a lot of difference in the design itself. So yes and no, depending on the ground problem that, or soil geotechnical problem that you're dealing with. I cannot give you an answer yes or no.
Okay.
I think sensitivity analysis is always a good idea, but not necessarily always necessary.
Yes.
Yeah.
Okay, then with this last question, we came to an end of this webinar with a lot of people registered, and I saw more than 200 really attending at this live webinar. I will thank you both, and also Georgia, for your presentations and your information. And for the audience, we have recorded this webinar, and it will be sent to everyone who has registered. And it is also to be found on several websites of ISMGGE and from NEN and so on. So thank you all for attending, and the people who are staying to the end, thank you for staying to the end. and hope to see you next time on the next topic of Eurocode 7 webinars.
Thank you. Bye-bye.
Thank you very much.
Bye.
Goodbye.